Morning, everybody. Welcome to class. Everyone's happy to be here, I assume. Tuesday morning, bright and early. Not too early. Okay, so how is everybody doing? Good?
Not really understand chapters 8 or 9, and I need to bring in, I don't know what that is.
Okay. So we can talk about chapters 8 and 9 today. We can look at the homework. We'll do that. What is the topic for this week? It's chapter 12, and that is the subject, what's called simple linear regression. And there are a whole bunch of videos on Blackboard in the, I guess it says the week 9-10 folder. So check those out if you haven't yet. I will talk a little bit about regression analysis today and kind of give some motivation for why it's done and what you can hope to get out of it, and then kind of to set the stage for what you're going to get into in stat201 when you learn about what's called multiple regression. And this is a very powerful, very well-used tool in business and science and just about anywhere you look. People are doing regression analysis. So let's talk a little bit about that, and then we'll turn our attention to the homework that's due this week. I guess that's homework number 7. And then we have just one more homework due next week, and that's going to be the one that focuses more on this regression stuff. So we're winding down. There's only one more quiz. That's quiz number 7. That's due this week at on Friday night, and then it's just the homework after that. Except for maybe you saw that I sent an email today about extra credit. So let me just make sure everybody understands what the deal is with that. You can get extra credit by doing the Learn Smart stuff on Blackboard. And if you do it all, you can get up to 1% bonus on your final grade. So after I calculate your final grade in the 2 different ways in which I do that, then I'll say how much of the Learn Smart did you finish. If you did it all, you get another 1 percentage point added on top of that. If you did half of the Learn Smart, then you get half a percentage point. If you did 1/10 of the Learn Smart, then you get 1/10 of a percentage point. Is that clear to everybody? So it has different questions it has you go through, and it keeps track of what things you've gotten right, what things you've gotten wrong, and then it goes through kind of the whole chapter and make sure you have all the material covered and understood. Yeah. So you got to complete and when you complete it, you get a score of 100%. So you got to complete the whole thing in order to get the 1% extra credit. Okay, so I mean, you know, this isn't enough extra credit to take you from a B to an A or a C to an A, but if you're kind of on the border between an A minus and an A, it might push you over. So any other questions about that?
So when you finish all the questions on
Right. Yep. So, okay. So let's talk a little bit about regression. So regression analysis is a general term for relationships between variables. So if we have the variable y, up to this point we've dealt with x's. We said if x is normally distributed, we can make inference on the population mean for x. Right, so we're going to do exactly the same thing with y, except for we're going to say that y now has some relationship to an x variable. And the simplest version of this is what I have written down here. This is called simple linear regression. We say that if we know what x is, and if there is a relationship between x and y, then I should be better off by knowing the relationship and plugging the value of x in to get a better estimate for y. So all we're trying to do here is the same thing that we did previously with x, and I don't want to confuse things too much, but let's just say that if y is normal with mean mu and standard deviation sigma, then we can do the one sample procedures on that. So forget about the relationship with x for a minute. We can do the same confidence intervals. For mu, for example, is going to be y bar plus or minus z times sigma over the square root of n. Right? It doesn't matter what we call the random variable. If we have just a single random variable, we can do this. We can do the hypothesis test that mu is equal to some value. And so where regression becomes powerful is if you think about something that we've said, I think, from day one, and that is that there's always some sort of uncertainty or randomness that's included in the data. Right? We might know what the mean is, mu, but there's always going to be some randomness, some inherent uncertainty. And you can think about that in terms of variability. The y variable, I mean, it's called a variable for a reason because there's variability in it. And we said that we can't ever predict randomness, or in other words, we can't explain the random part of the y variable. But there are parts of the y variable that we might be able to explain. In other words, some of the variation in the y might be due to some other variable. And in fact, when we're doing regression analysis, that's exactly what we're saying. Can we explain some of what's going on in the y variable by knowing what the x variable is? Now, this error term over here, that says there's still some random parts. There's still things that we can't estimate. And so with regression analysis, all we're trying to do is say, let's estimate y, but let's use x to help us get a better estimate. Okay, so in regression analysis, so this is what we call this single sample. So the chapter, I guess it was chapter 8, chapter 9 stuff we did, hypothesis testing and regression analysis, or not, confidence intervals. If we're talking about regression analysis, what we're saying is that the average value of y, mu sub y, is beta 0 plus beta 1 times the x. And we're saying the standard deviation of y is just going to be sigma. Okay, so how does this work? In this context, we'd say y is normal with a mean mu sub y and a standard deviation sigma, which means that our error term, this part right here, is going to be normal with mean 0 and standard deviation sigma. Why is that? Because if I know what x is, so given x, I plug it into that formula, I get the mean. But that doesn't take into account the randomness. So I still need to allow for there to be randomness. And I'm never going to be able to predict the random parts. So when we're doing single sample analysis, oftentimes you might be able to say, well, there's a lot of variation. Some of it's random, but probably not all of it's random. I can probably come up with some variable that would help me explain the variation in the y variable. Okay, so all we do with regression analysis is we're going to say, look, if all things being equal, the simplest explanation tends to be the best explanation, or the correct explanation. Has anybody ever heard that term before, or that idea? It's called Occam's razor. I'm sure you have. People always are telling you, look, just keep it simple, right? The simpler the explanation, the better. You get into these convoluted, crazy theories and explanations, and pretty soon nobody knows what's going on. So the idea behind regression analysis is, if all things are equal, then we're going to say there's not a relationship between the x and y. In other words, if I have these two different approaches right here and right here, if they give me the same information, then why would I use the more complicated one? Well, I wouldn't. So it turns out the null hypothesis with regression analysis is that beta 1 is equal to 0. And all that says is there is no relationship between the x and the y. Okay, so just like all the other things we did with hypothesis testing, we're going to assume that's true, and then what? We're going to collect some data and see what the data says. Does the data support the null hypothesis, or does it support the alternative hypothesis? And so there's going to be confidence intervals, there's going to be test statistics, critical values, all the same stuff that we've already learned about. We're just going to apply it in a slightly different manner here. So if we're going to do a hypothesis test, what do we need? We need an alpha level, we need a null hypothesis, we need a test statistic, we need a critical value, or if we want to use a p-value approach, we can use a p-value. So if I want to test this hypothesis, and what the hypothesis again is really saying is that there is no relationship. I mean, who's ever been in a relationship? Right? So it's Friday night, your person you're in the relationship with says, hey, let's go to the movies. Is that simple, or is that complicated? Okay, it has the potential to be very complicated, doesn't it? Right? I mean, I want to go see some movie, you want to go see a different movie, so you got to agree on things. I'm not saying it's bad, it's good, actually, to be interacting with people and having relationships and that sort of thing. But it's not as simple as just saying, look, I'm going to do whatever I want. This is the movie I want to see. I don't have to worry about anything. I'm just going to go do that. So anytime there's a relationship, things get more complicated. And unless there's a benefit, why would you make things more complicated? You wouldn't. And that's exactly the logic that's going on here. If there's no benefit in having this relationship or understanding the relationship or establishing that there's a relationship, let's just use the case where there is no relationship. Right? So what's the test statistic we have here? For the null hypothesis, we have a t, random variable. And this is going to be based on, well, anytime we have a Greek letter, what does that tell us? Greek letters are parameters, right? And parameters are characteristics of populations, and they're unknown, and they're unknowable, and that's what we're trying to estimate. So if we can estimate beta 1, that tells us what the slope is. So for a 1 unit change in x, think about the slope intercept form of a line that you learned about in junior high or high school or wherever you learned about that. if we know what the slope is, then we know what the relationship is. So if x changes by 1 unit, then y is going to change on average by beta 1 units. All right, so if it goes up, if it goes down, whatever the case may be, I need to know what that beta 1 is. Beta 1 is 0. That says doesn't matter what happens with x, there's no effect on the y. So we're going to estimate beta 0 and beta 1 with what are called the least squared estimates. So we're going to say y hat is b0 plus b1 times x. So just like we said, x bar is our estimate for mu, p is our estimate for pi. We're going to say b0 is our estimate for beta 0, b1 is our estimate for b1. And once we do that, we can say, well, if the null hypothesis is true, and I take b1 and I subtract that hypothesized value, which is 0 in this case, and I divide it by the standard error of the estimate, then we get a t random variable. And this is our test statistic. So if I know what the test statistic is, and I know what the distribution is that it comes from, you guys should be saying, oh yeah, that makes sense, because we already did that. We said, well, let's just put this in perspective. If we have just a one sample procedure, we would say we're going to estimate mu with x bar. All right, we're going to say x bar is our best guess for mu, and so if we do the hypothesis test that says mu is equal to mu 0, what's our test statistic? It's going to be z, which is x bar minus mu 0 divided by sigma over the square root of n. So we know what the parameter is that we're interested in. In this case, it's the mean. And we know what the test statistic is, so we can compare this to critical value. Right, we have these rejection regions. And we say, where does the z lie? We have mu 0 right here in the middle. Well, the same thing's going on over here. Except for now, I'm not talking necessarily about mu. I'm talking about B1 and beta 1. I mean, this would be my estimate, B0 plus B1 times x. But the null hypothesis that I'm testing is not for mu. I'm not saying mu is equal to 0. Instead, I'm saying beta 1 is equal to, in this case, we're saying 0. You could put in some other number here if you wanted. Say beta 1, 0. Come up with whatever you think the slope might be, but the general case is when beta 1 is equal to 0. So what's our test statistic? It's b1 minus 0 divided by the standard error, s of b1. All right, so do I know how to calculate this thing over here? Yeah. And I look and see, does it lie in the rejection region? Well, the same thing happens over here. This is a t random variable, and it actually has n minus 2 degrees of freedom. Now before, when we did the one sample procedure, we said we had a t on n minus 1 degrees of freedom. But now we've got two parameters, beta 0 and beta 1, that we're estimating, so we lose 2 degrees of freedom. And so here's our rejection region. We've got 0 in the middle and another rejection region. So in terms of the mechanics of the hypothesis test, these are all the same. In fact, anytime you do a hypothesis test, all you need is to ask, what's the hypothesis? What's the alpha level? What's the test statistic? And that tells you the critical values and everything else. So the procedures, I mean, it's the same story over and over and over and over again. Right? Is it Harry Potter or is it Luke Skywalker? Well, Harry Potter wears glasses, Luke doesn't, but they're both trained by a wise old man, never knew their parents, super whiny, good at flying. You know, they have all these things in common, but it's still, you know, different because the details are different. But it's the same exact thing that's going on here. So, so what are the implications of this? If beta 1 is equal to 0, that says forget about x. There's no relationship that's meaningful. So all the variation that we see in the y variable, we're going to attribute to randomness. If we reject the null hypothesis, on the other hand, then what does that mean? Well, let's look at some fake data. All right, here's a nice little data set that I'm making up as we go. If there's no relationship between x and y, then y bar is going to be my best guess for the average value of the y's. All right, so I just draw a line right here. So that's my best guess. Confidence intervals, how do I create a confidence interval for this? Confidence interval basically says how much of the variation, or how much of the, or how big are the is this band, and that tells me something about the variation, and then I would divide that by the square root of n, and that would give me these the confidence interval is going to be closer to y bar than what I've got drawn here. So this range of the y's leads me to the sample standard deviation, which you'll remember is the square root of the summation of xi minus x bar squared over n minus 1. Right? So again, think of the one sample procedure that we learned about in chapter 8 and chapter 9. Okay, so I've got a pretty big measure for the variability if I don't take into account the x variable, right? Can everybody see that from here? This is what we're doing. Okay, so the question is, does it help to know what the x variable is? And when I say does it help, I mean, can we reduce our estimate for the variation? Or can we pick up some of the signal that's in the variation in the y variable from knowing x? So let me see, let's change colors here. In other words, if I came over here and said this is the line that best fits the data, let's try a better one. Does that help me? Yeah, well, in this case, I would say, how much variation is there above and below that line? So I'm actually measuring in this distance here, right? So, so this is going to be a different estimate for S, and we'll call it S sub E. And instead of calculating it using this other formula over here, we're going to take the summation of, sorry, I wrote X and I should have written Y, shouldn't I? Let me change that. Yi minus Y bar. All I'm doing here is saying, instead of having Y bar as my estimate, I'm going to use Y hat. So I have Yi minus Y hat quantity squared, and then I'm going to divide by n minus 2 instead of divided by n minus 1. And again, that's because Y hat is the equation of the line, b0 plus b1 times x. That's the line that best fits that data according to what's called the least squares criterion. And you're gonna, if you haven't looked at the videos yet, go and look at those. I'm just kind of going through the story here in not great detail, but the details are there, and it's in the textbook as well. But the idea here is, if I can do better, if this estimate for the error is less than the estimate for the standard deviation without the straight line, without the regression equation, then that answers the question whether I'm better off making the assumption that I have a complicated relationship. Remember, we said if there's a relationship, it's going to be more complicated. And we're only going to do that, we're only going to go with the relationship if there's some benefit. And the benefit we get is a reduction in the variability in the y variable. In other words, we're able to explain more of the variability in the y variable with x. That leads to a smaller error. And if that's the case, then we're going to reject the null hypothesis and say that beta 1 is not equal to 0. So that's what's going on here. And you'll find as you learn more about regression and the other statistical tools that are out there, what you're really trying to do when you go to extract information from data is you're trying to explain the variability. So if y varies a bunch, I know part of that's due to randomness, but part of it might be due to the relationship it has with some other variable. And so if we can establish that using statistical methods, is there a statistically significant evidence that tells us that beta 1 is not equal to 0, then we can use that to make decisions. And in fact, if I wanted to estimate the value of y, if I want mu, and I don't know that there's a relationship between x and y, the best I can do is y bar plus or minus z times sigma over the square root of n. All right, that's a confidence interval for mu. If I know there is a relationship, then I get a confidence, so if x, let's say if x helps, then we're going to get y hat, that's going to be our estimate. And that's b0 plus b1 times x plus or minus t times, this is where it actually gets a little bit unwieldy, but t times the standard error, SE, and then it's not actually as straightforward as it looks. It's going to be 1 over n plus, now it depends on the value of x, so xi minus x bar squared divided by what's called the sum of squares for the x's. But you can see the formula is basically the same. We're saying here's our point estimator plus what's the random variable, what's the test statistic, it's a t distribution instead of a z, and now we multiply that by the standard error of y hat of the point estimator. And this is where it gets a little bit more involved, but this interval here is going to be much smaller than the other one if there's a linear relationship. And so you're not only getting a more precise estimate, you're doing it with, I guess more precise means that the variation is smaller. So you're getting an estimate, a better estimate with smaller variation if there's a relationship. Okay, so questions about that? This is kind of big picture, I know. If you haven't looked at all the details in the week 9 folder, videos and the stuff from the textbook, then I encourage you to do that because this is important stuff. So what do you get into once you learn how to deal with this? If you say y is equal to beta 0 plus beta 1 times x, how do you think you could build on this model? So let's use an example here. Let's say y is price of a house. Right, you guys, when you graduate from college and you get jobs and you move off somewhere, you're going to want to buy a house some point in your lives probably. So how can you explain the price of a house? What variables, what x variable could we use to explain the price of a house? There's a lot of them. What about the size of the house? The bigger the house, the more material goes into the house, the more it costs to build the house, the more labor it takes, so forth. The bigger the house, the bigger the footprint of the house, which means you got to have more land maybe. So size of the house, that could be our x. So do you think that if we know the size of the house, that's going to help us predict the price of the house? Probably. Yeah. It depends on the data. We'd have to actually go in and perform the test to see for sure, but it makes sense. So we're going to call that x1 and put a 1 right here. Why would we say x1? Because we're going to look for an x2. Is there another variable we could use to help us predict the size or the price of a house? What do you guys think? Yeah, what?
Renovations.
Okay, so maybe the age of the house or the age of the work that's been done in the house. Okay, so we can just throw that in here, and now we have what's called multiple regression. I'm not going to go into any of the details on this because it's a topic for stat202, but I do want to let you know that this is an extremely powerful tool. I'm sure you can think of other variables. What other variables could we put into this model?
Location.
Okay, so x3, we could have some sort of location. Plus what else? Maybe the number of bedrooms. Put that in. Beta 4, x4, plus what else? Number of bathrooms. Does it have a pool? Is it a corner lot? Is it a cul-de-sac? Is it, what's the size of the neighbors' houses? How many, does it have a garage? Does it have a 1-car garage, 2-car, 3-car, so forth? So you see, you can keep adding all sorts of variables in here. We'll just say there's P of those things. But what do we also have to add in? We are still going to have randomness. There's still going to be error. Or at least there should be. And this is where you can run into trouble, because it turns out that if you have n data points, n observations, and you have n x variables, then you can explain all of the variation of the y variable. And the error term goes to 0, and that's completely unrealistic. So that Occam's razor thing really comes into play here. If I know the size of the house, does that contain the same information as the number of bedrooms? Well, not exactly, but if I've got 5 bedrooms, the house is probably pretty big, right, in order to support that. So sometimes there's redundant information that we don't want in the model twice because we want to keep things as simple as possible. If it has 5 bedrooms, how many bathrooms is it going to have? Probably more than 1 or 2. Right, so there's relationships between those things. So we have to look at the relationship between the x variables as well as the relationship between the x and the y's. And again, that's for a different course, stat201. And when you get into your finance classes and accounting and marketing, then you have to worrying about that. Okay, but let's just talk about correlation for a second. I mentioned the correlation between the x's, but what we're really interested in simple regression is the correlation between x and y. So what is the correlation? So remember, right, we talked about that earlier. It's the measure of what? Measure of the strength of the linear relationship between 2 variables. So rho is the population correlation. And there's a formula you can use to write down R, which is the sample correlation. And what is the null hypothesis that beta 1 equals 0 imply about the population correlation? So if beta 1 is equal to 0, it means there's no relationship between x and y. So this means exactly the same thing as saying, let's test the null hypothesis that rho is equal to 0. Okay, so there's a test statistic, T, and let's see if I can remember it off the top of my head. I can't remember off the top of my head, but it's got the correlation in it, R, and turns out it is exactly the same thing as the T that we had previously, B1 minus 0 divided by S of B1. Although when you see the formula for it, you're going to say, how are those things the same? And in order to answer that question, you have to look at the formula for B1. So B1 turns out to be the summation of xi minus x bar times yi minus y bar divided by the summation of xi minus x bar quantity squared. And the error for that thing is a more complicated formula that I'm not going to make you memorize. You don't need to put it on your cheat sheet for the final exam. But when you work it all out, these things do turn out to be the same. So there's 2 ways to think about this simple regression. I'm testing whether the correlation is equal to 0, or I'm testing whether the coefficient in the regression line is equal to 0. And they turn out to be equivalent. There's one other way to test this, and that's with what's called an F-test. And actually, I'll talk about that in just a few minutes. So one thing that you run into often is called the coefficient of determination, or the R squared value. So R squared is the measure of the proportion of the total variation in the y variable that is explained by the regression line. Okay, so if you come back here and you say, how much variation is there in the y? We can get that by looking at the what's called sum of squares for the y, which is summation of yi minus y bar quantity squared. And that shows up here, right? If we divide that by degrees of freedom and then take the square root, that gives us an estimate for the variation. Right? So that's the most variation there is in the y variable. Okay, if I use the line y bar instead of y hat, that's the biggest the measurement of variation is going to be. So if I take that and I say, of that, how much is explained by the regression line? So we've got the summation of yi minus y bar quantity squared. How much of that is explained by the regression line? This is going to be the summation of y bar, we'll say y hat minus y bar quantity squared, which is just 1 minus the summation of yi minus y hat quantity squared divided by summation of yi minus y bar quantity squared. So what does all this stuff mean? This right here, yi hat minus y bar, that says, let's come back, let's draw a new picture because that was kind of messy. We'll just use like a few points. Okay, so if I've got these data points, and that's my fitted line, and here's the average, and I wanted to know the distance between here and here, that's yi minus y bar. And if I square that and add all those things up, then I get the total sum of squares. So how much of that is error if I use the regression line? Well, the error part is from here up to here. So that's yi minus y hat. That's the part that we're attributing to randomness. So if we're attributing that part to randomness, what's this other part being attributed to? This is y hat minus y bar. So that's the part of the variation in the y variable that's being explained by the x variable. So if I want to know the total amount of variation, that's that measure. So if I square that and add it all up, then I get the total sum of squares. How much of that total sum of squares does the regression line explain? Well, it's just going to be take this part here, square that, sum it up, and divide it by total sum of squares, which is exactly what we're doing right here. So this is called the regression sum of squares divided by the total sum of squares. Another way to think of that is 1 minus the error sum of squares divided by total sum of squares. Okay, so r squared is important. It's something that's always between 1 or 0 and 1. You might say, well, what's a good value for r squared to be? Well, the bigger it is, the more explanatory power your model has, the more information you're going to get out of it. But sometimes even small numbers for r squared can be informative. Like if you had an r squared around 95%, you'd say, yeah, I really want to know what x is because that's going to help me explain y, and I should be better off. But if your r squared is only 5%, in some situations, that still might be helpful. If you're trying to determine how to invest $1 billion, and you can explain 5% of the variation in the decision process, 5% of $1 billion, that's a lot of money. So you don't want to throw that information out just because it's got a low R squared. So it's kind of dependent on the context of the question as to whether your R squared is good or not. And turns out R squared is the square of sample correlation, and that makes sense, at least in simple regression. Okay, so excuse me. Questions about this? We'll consider this then like a what do they call those things? A trailer. It's like a movie trailer. You get the short version of it, the exciting parts, and you get to watch the rest of the movie and fill in the rest of the details. But we will talk more about this next week too. So let's turn our attention to the chapter 8 and 9 questions that people have. So in particular, let's look at homework number 7 and or other questions you might have about any of that.
I sent you that email about the t-test or whatever, the z, but I was still a little bit confused. Like, is on some of the, is there like a specific rule, like when the sample size is above 30 or something? Because like,
yeah, so some people will say, so here, let me pull up the t table. So the question is, if you're not so you're not out in the dark here, the question is, when do you use the t instead of the z, or when might you use the z in place of the t? And let's pull up the t table. So the t table and for this class looks like this. You can see that it has degrees of freedom starting at 1, going all the way to 50 for every sample size. So remember what we're saying. So let's write this out. We have so for one sample, procedures for the mean. If x is normal with mean mu and standard deviation sigma, wait a second, I think I made a mistake way back here. Oh no, then we say, okay, do we know sigma? If we don't know what sigma is, then when we go, if we say z is equal to x bar minus mu divided by sigma over the square root of n. Okay, that's always true. But the question is, do I know what sigma is? So is sigma known? If so, then I'm going to do that. If not, then what am I going to do? I'm going to use the t, which says I have x bar minus mu divided by s over the square root of n. But the t distribution depends on degrees of freedom. So how big is the sample? Another way to think about that is, how much information do we have? So if I have this t random variable, I'm going to say, this is what it looks like. Well, it kind of looks like a normal distribution. In fact, if I didn't draw a normal distribution on here, you wouldn't be able to tell that this is a t. Okay, so it turns out that as n gets large, then the t converges to a z. And so the question is, how big does n have to be before we're going to say, let's just use the normal distribution for this? And that's a good question that I don't think people agree on generally. If you're using a computer if you're using Excel, then you can put any degrees of freedom that you want. So let's say t dot inverse probability. Let's say we want 0.975. I mean, with this, I can put in any degrees of freedom I want. In fact, they don't even have to be integer degrees of freedom. I can put in let's say 12.8. If I do that, it's going to give me back a number. Now, I'm never going to have 12.8 in this setting, so put in 120. You see it's still not quite the same as the normal. What would the normal be for that same thing? So norm.s.inverse 0.975. You get 1.6, basically, 1.96. So even if I have 120 degrees of freedom, I still don't have exactly the same. But as that degrees of freedom gets bigger and bigger, then those things will converge. And let's just prove that by plugging in like 12,000. So 12,000 degrees of freedom, now they're getting closer and closer to each other. So to answer your question, the rule of thumb is go to the table that you have available to you. If the degrees of freedom are higher than, the maximum degrees of freedom are higher than the sample size, then use the t. Or if you're using the computer, just always use the t, because the computer will handle any degrees of freedom. And you can see here the normal values are given in that last column with infinite degrees of freedom.
But if you know standard deviation, or if you know sigma.
If you know sigma, then use z. Always use z. Yeah.
So this table is what's used for all the homework, right?
You should be able to use this for all the homework, yeah.
Where is it?
It's Appendix D in the textbook. But you see here, the problem with this is once you hit 50 degrees of freedom, then it jumps to 55. Let me zoom in here so you can see a little better. All right, once you hit 50, then it jumps to 55, and then 60. So now you've got to start interpolating. Say well, I've got 53 degrees of freedom. That's somewhere between 1.29 and 297 and 1.299. And so I could use 1.298 if I like. The real value is not 1.298. In fact, there's some rounding going on here as well. A lot of textbooks use, they have degrees of freedom that just go up to 30. And once you hit 30, then it jumps to 40, 50, 60, 70, and then 100 maybe, and then it'll go to infinity. So in practice, you can, if you have a computer, again, just let the computer do it. But look at your chart. If your chart doesn't go up that high, then use the normal. Okay, so other questions about that? Is that clear then? I mean, I tried to explain that in that email I wrote you back, but
it's just like because it's on Connect, it's like if you don't, because I know like sometimes the differences are so minute, like using 1.98, 1.95, it's just like the way that
right. So
wrong.
So Connect does on questions like that where there is ambiguity, it will make the margin of error bigger. Yeah. Or I think it will also put in multiple correct answers. Yeah. But you know, if you run into a problem with that, just send me email and I'll check it out. And because you're right, it's a kind of a pain in the neck to have to worry about that. So I find it best, even with Connect, just to use the computer, use Excel to do all that. Okay, so homework 7. Questions from homework 7?
4, 5.
13, 14, and 16. Okay, that's a pretty good start. Do you guys want to take a break before we jump into this? Raise your hand if you want to break or don't want to break. All right, let's take a short break. We'll do 5 minutes, and then we'll jump in, and we should be able to get this done a little bit early. So we'll start back up at 11 o'clock. So question number 5 from the homework says the Scottsdale Fire Department aims to respond to fire calls in 7 minutes or less on average. Response times are normally distributed with a standard deviation of 1 minute 42 seconds. Would a sample of 18 fire calls with a mean response of 7 minutes 21 seconds provide sufficient evidence to show that the goal is not being met at the alpha equals 1% level? So the first thing we're asked to do is to find the appropriate null hypothesis. And so when we talk about null hypotheses, what are we saying? We're going to say, let's give the benefit of the doubt to the claim that's being made. Or rather, not the claim necessarily, but think about this fire department. They've spent a lot of time and effort and energy coordinating their processes and everything that goes into this so that the response time is less than 7 minutes, or less than or equal to 7 minutes. Right? That's what they trained for. So we're going to say, okay, let's give them the benefit of the doubt, because if they're doing what they are training themselves to do, then they don't need to make any changes. So the alternative hypothesis says changes need to be made. So in this case, we're going to say, well, if their null hypothesis is true, that means that they're actually able to do this. Their mean response time is less than or equal to 7 minutes. And it says right here, 7 minutes or less. So that should be the hint to you that that's signifying the null hypothesis, right? Because the null hypothesis always has an equal sign in it. So A should be the right answer for that one. And B says that mu is greater than or equal to 7. But that would say business as usual, the way we are doing things, gives us a response time that's bigger than or equal to 7. And that's not what the goal is. The goal is that it's less than or equal to 7. Does that make sense, the way to think about that? Okay, so again, null hypothesis says there's we'll give the benefit of the doubt to whatever the established policies are, and think about it in terms of machines that are building parts. We're going to assume the machines are doing what they're supposed to do. They're producing parts that are in spec. Okay, so what's going on here? We get a sample of size 18, and we know that we have, this is number 5. We're going to test the null hypothesis that mu is less than or equal to 7 versus the alternative that mu is greater than 7. We have a value of x bar, which is going to be what? 7 minutes 21 seconds. So what does that mean? 7 plus 21 over 60. So we're going to need to calculate that. We know that x is normal with mean mu and standard deviation sigma. And standard deviation, so this is given to us, 1 minute 42 seconds. So sigma is equal to 1 plus 42 over 60. So we'll need to calculate that to get that in the decimal form. And what else do we need to know here? They want to know what the rejection region looks like if alpha is 1%. So alpha 0.01, and we have a right tail test. So if you can draw the picture, you should draw the picture. And if you can't draw the picture, figure out how to draw the picture. In this case, we're going to say the null hypothesis says the mean is 7, And the alternative says we have something in the right tail. So we go up here at the alpha level, 1% of the area is to the right of what value? So the rejection region is anything bigger than this critical value, and this is in the X bar world. In the Z world, 7 gets transformed to a 0, and the critical value gets transformed to what? Well, they kind of tell us here because it shows up in both of these options. So it's 2.33 or 2.326. So this is 2.326. That's in the Z world. If I want to convert that to the X bar world, what do I get? 7 plus 2.326 times what? Sigma over the square root of n. Now I haven't figured out what sigma is yet, so I'll have to do that in just a second. Okay, so there's our rejection region, and so what did we observe? We observed 7 plus 21 over 60. That's like 7.3 something. Right, 7.35 probably. So from the random sample size 18, we observed something bigger than 7. So the question is that difference, that 0.35 of a minute, 21 seconds that we were over time, is that a big difference? Is that statistically significant? Whether or not it's practically significant, I don't know. I guess it depends if you have little kids burn inside this building that's burning, and 21 seconds might make the difference. But statistically, is that significant? Well, that's the question. We want to know, does this 7.35, does it lie above this critical value? And if it does, that means there's something wrong with the process, something wrong with what they're doing. They need to make some changes. So just because it's bigger than 7 doesn't necessarily mean that it's significantly bigger. In other words, if it's not significantly bigger, then the difference we see is due to randomness. Remember, we talked about randomness and error that we have to always keep in mind. So we have two options. We can either take this number here, X bar, and convert it into Z, see where it lies, or we can take our critical value here, 2.326, and convert that into the X bar world. So either way, I'm going to need to know what my sigma value is, and it's going to be like 1.7 or something, but we'll come over here and throw these things in. So homework, 7.5. Let's see, what do we have? Mu 0, we have X bar, we have sigma, we have alpha, we got the Z critical value, the X bar, critical value, and we've got the Z, we'll call it Z calc. All right, so let's just throw these numbers in. 7, X bar is equal to 7 plus 21 over 60, so 7.35. Sigma is equal to 1 plus 42 over 60, 1.7. Alpha is 0.01. So the Z critical value is going to be norm dot inverse dot S dot inverse 1 minus alpha. Why is it not 1 minus alpha over 2? 1 minus alpha, because it's a one-tailed test. If it were a two-tailed test, we'd have to say, well, half of that area is in the left tail, but we just have a right tail test, okay? So our x bar then is going to be equal to mu 0 plus z times sigma over the square root of n, which we haven't put in yet, so let's just say it's going to be d7, and we're now going to insert everything over, so n is 18. And that doesn't look quite right, so let's E7, so that should be D7. And everything else should be good. So we got mu plus F7, that's critical value, times sigma 1.7 over the square root of 18. So we see that the critical value is 7.93. And so what did we observe? We observed 7.35. So 7.35 is right here somewhere. So are we in the rejection region? No, we're not in the rejection region. Does that mean we are not going to reject? It means we're not going to reject. Does that mean that the null hypothesis is true? What do you think? Does that mean the null hypothesis is true? Have you ever known anybody that makes decisions and when they make a decision they're right every single time? You probably know somebody who thinks that they're right every single time, because you know me. At least my kids will tell you I think that way. But it's not true. It doesn't mean it's correct. It just means we don't have evidence to reject the null hypothesis. Maybe it's not true. Maybe the average response time is bigger than 7, but the evidence that we collected supports the null hypothesis. So we're going to go with the null hypothesis and maybe do that with a grain of salt. Okay, so critical value of the test statistic in Z. Well, that's kind of stupid. They just gave us that number. And, oh, sorry. Calculate the value of the test statistic. So I did not do that. So the value of the test statistic is this 7.35 converted to the Z world. So this is going to be 7.35 minus 7 divided by sigma over the square root of n. So I need to do that. This is going to be equal to the quantity x bar minus mu 0 divided by sigma over the square root of n. So we have 0.87 standard deviations. Seven, 3, 4. And we'll just leave it at that. And if they tell us we rounded wrong, we'll deal with that in a minute. Okay, then part C says use Excel to find the p-value. So the p-value is the area under the curve, bigger than what we observed. So we know how to find areas under the curve for normal distribution, right? So we're going to use Excel to do that, get the p-value. You can also look this up in the chart in the book. We're going to take 1 minus norm.s.dist. We're going to put in our z calculated, and we say we want cumulative. Why are we doing 1 minus? Because norm.s.dis gives us the left tail. We want the right tail. So our p-value is about 19%. Okay, so if alpha is 1%, are we going to reject the null hypothesis or not reject? We already said we're not going to reject, so fail to reject. So incidentally, what value of alpha would I need in order to reject the null hypothesis? Remember, alpha is a subjective quantity. What are you comfortable with for a probability of making a type 1 error? 5% is the number that's used most often, but 1%, 10%, you can use any number you want between 0 and 1. Sorry, 0 and 1, 0 and 100%. So what value of alpha do we need in order to reject the null hypothesis? Well, it's got to be anything bigger than the p-value. It's got to be 19.2%. 19 point or whatever it is. Anything bigger than that. Okay, so let's check our work. And looks like we got it right. Okay, good. Question number 6. Is that the next one we want to see? Oh, no, number 4. Sorry, I went out of order. Let's go back to 4 then. Okay, the mean arrival rate of flights at O'Hare Airport in marginal weather is 195 flights per hour with a historical standard deviation of 14 flights. To increase arrivals, the new air traffic control procedure is implemented in the next 30 days of marginal weather. The mean arrival rate is 198 flights per hour. Okay, so you can see how this is set up. They're saying 195 flights per hour with certain standard deviation. That's how things are, right? When we look back at history and using the current system, but they want to increase that. So what are they going to do? They come up with some new procedures. So the null hypothesis says that the new procedures aren't any different than the old procedures. Why would we say that? Because the alternative hypothesis tells us that we have to do things that are painful, like make changes, like retrain people, and that's no fun. People just like to do, I mean, human nature is, let's just keep doing things the way we're doing them. No one likes change because it gets you uncomfortable, out of your, it makes you do things differently, and people don't like that. So we're not going to implement these changes if they're not really going to help. Okay, so they just do a trial. Okay, well, let's just test this out and see if it works. And they get 198 flights per hour as opposed to 195 flights. So 198 is bigger than 195, isn't it? Yeah. So shouldn't we go with the new way? Because 198 is bigger than 195. That's the question. Well, it's bigger, yeah, but how much bigger? Is it statistically significantly bigger, or is it just bigger due to randomness? Can we attribute that difference to chance? So we're going to set up the null hypothesis. The null hypothesis says that the new mean, or that the mean is not any bigger than what we were doing before. The alternative hypothesis says that the mean actually is bigger. And so we're going to draw the picture. Again, we've got a right-tailed test. Here's 195. And what's the alpha level here? Okay. So set up a right-tailed test to alpha equals. So they're telling us to use 2.5% for alpha. So here's 2.5%, 0.025. In the X bar world, we have 195 as the mean and some critical value. In the Z world, we have 0, and what's this? 1.96. So the critical value in the Z world is 1.96. In the X bar world, it's going to be 195 plus 1.96 times sigma over the square root of n. And in this case, n is equal to 30, and sigma, we know what sigma is? Yeah, we know what sigma is because they told us right here it's 14. 14 flights. So we get 14 over the square root of 30. Okay, so null hypothesis is that mu is less than or equal to 195. That's D. Reject if Z is bigger than 1.96. Okay. Calculate the test statistic. Now, if they don't tell you what they mean by test statistic, usually that's the Z version of this thing, or the T version. Are we doing a T or are we doing a Z here? This is a Z. Why is it a Z? Because we know what sigma is. Okay. Doesn't have to do with the fact that they told us there's 30 data points, right? There's 30 of these things here. They give us the data, we can actually click on this if we want and pull it down. But since they told us what the standard deviation is, there's actually no reason to do that. The mean, we're also told 198. So I don't have to mess with that data if I don't want to. And in fact, I'm not going to. But I am going to come over here to Excel. And I'm just going to copy all this. Paste it. And then I'm going to change this to 7.4. So mu is going to be, what's mu 0? 195. X bar is 198. Sigma is 14. N is 30. Alpha is 0.025. And so my Z value, my Z critical value, or my test statistic is 1.17. How do I know they're not asking me for 198? I mean, that's also the test statistic. Well, because they gave me 198. And it's just sitting right there. So they're not going to ask me to just copy and paste something straight from the question. Okay, so there's our test statistic. What's the conclusion? So what's the conclusion of the test? If we come over here, sorry, let's see, 1.17. So 1.17 is right here, 1.17. So what's the conclusion? Are we going to reject the null hypothesis? Well, this is the rejection region. So what we observe is not in the rejection region. So we're not going to reject, which means that this new procedure doesn't do any better than the old one. The difference we saw, the 3 extra flights per hour we saw in that sample size 30, is just randomness. It's just because of random variation. That's the conclusion we make. Now, are we right? Maybe. Probably, but so there's not been a significant increase in the average number of flight departures. Would the decision have been different if you used alpha as 1%? So here we used alpha as 2.5%. What happens if alpha is 1%? That puts the critical value out further in the tail. So instead of here, we would have something out here, which makes the rejection region smaller. So that doesn't really do anything for us. So here's the right answer. This question's a little bit confusing. There's A and there's B, but neither of those. So we'll say no. I don't know why they gave us A and B, but what assumptions are you making, if any? Our sample size is 30. All right, so scroll up here. Sample size is 30, so the central limit theorem kicks in here. So we don't actually have to make any assumptions about whether we have normal data. And so let's click that and see how we did. Okay, well, central limit theorem being what it is, I would have gone with this one, but they're saying it wrong, so. So I'll go with that one. And not necessarily that we have a normal population, but I guess the not badly skewed one. But the central limit theorem does say if you have your sample size big enough, then it doesn't matter what the distribution is underlying. Okay, so questions about that? We're good? So this is kind of the process you go through over and over and over again. So let's look at the next one, 13. And we'll try and do this one a little bit faster. Let's see what's going on. All right, to combat antibiotic resistance, Quality Improvement Consortium recommends a throat swab to confirm strep throat before a physician prescribes antibiotics to children under age 5. In a random sample of 100 children who receive antibiotics for throat infections, 30 did not have a throat swab at 5% alpha level. Is this a statistically significant reduction over last year's national rate of 40%? Okay, so how do we set this up? What's the null hypothesis? Well, what was going on last year? They were not recommending these swabs, right? So people would just go into the doctor and the doctor would say, oh, it looks like strep throat. Here's your prescription for your antibiotics. And so that was 40% of the 40% did not have the. So hold on a second. Okay, so I don't know if this really makes sense or not, but last year they had 40%, right? And so they're measuring whether what happened this year is different than that. So if it's gone down, then that's going to be the alternative hypothesis. So 40% was last year, and we're testing whether we have a reduction. So should be this one here, pi 1 is less than 40%. So what kind of test are we doing here? The pi gives us a hint that this is going to be test for proportions. And we know that the null hypothesis says that pi is greater than or equal to 0.4. The alternative is that pi is less than 0.4. And what other information do we have? We have n is equal to 100. The sample proportion p is 0.3. And alpha 0.05. So what kind of test do we have here? This is a left tail test. The mean is 0.4, and we have 0.05. Tells us that the rejection region is anything less than what's going to be 1.5 1.645 in the Z world. In the P world, we can find out what that number is if we want. Are they asking us to do that? Calculate the critical value. Okay, so the critical value should be 1.645. Sorry, negative 1.645. I drew that wrong. Negative 1.645. And then they want us to calculate the test statistic. So what's the test statistic? Test statistic is going to be P minus pi 0 divided by the square root of pi 0 times 1 minus pi 0 all over n. So that's the Z calculated value, Z calc. So let's go over here to Excel and start plugging stuff in. So homework 7.13, we have first of all pi 0, we have P, we have N, alpha, and plug these things in. Pi 0 is 0.4, P is 0.3, N is 100, alpha is 0.05, and so our Z critical value is going to be norm.s.inverse, put in 0.05, so there's the negative 1.645. If I want to convert that to the P world, proportion world, I'll say P crit, that's going to be equal to the mean plus the Z value times the square root of pi 0 times 1 minus pi 0 divided by N. So here we have 0.3194. This is 0.3194. All right, so what are they asking for here? The test statistic. What's our test statistic? Our test statistic is going to be the Z value associated with 0.3. So if we put in 0.3, we're going to get the Z calc. So that's 0.3 minus 0.4 divided by the square root of 0.4 times 1 minus 0.4 over 100. So let's come over here. The calc is going to be equal to the quantity P minus pi 0 divided by the square root of pi 0 times 1 minus pi 0 divided by N. So I have negative 0.204 and, sorry, negative 2.04. So that's 2 standard deviations below the mean, and so that's clearly in the rejection region. I knew that once I figured out what the critical value was. So I'm going to reject the null hypothesis, and then the question, is it safe to assume normality of the sample proportion P? And what do we know about the central limit theorem when it comes to the proportion? We have to have n times p and n times pi and n times 1 minus pi both bigger than 5. And in this case we have 30 out of 100, and so that means we have 70, 30, and 70. So yes, we can say that's justified. And let's check our work. And looks good. Okay, so the next question, 14. So this one's very similar. Coin was flipped 13 times and came up heads 8 times. The assumption of normality is justified. I just barely talked about that. 13, we had 8 successes, so how many failures did we have? 5, so it's right on the border, but we should be okay. Let's just say yes and see what they agree with us. Okay, so it's got to be greater than 5. Must be. It's got to be greater than 5. I don't. You have to look at the details on that. So we'll change that to no. Calculate the p-value for the observed sample using the normal distribution. So this is 14. We have the null hypothesis says the coin is fair. So pi is equal to 0.5. The alternative hypothesis says the coin is not fair. And for part B, they say let P be the number of successes divided by the sample size, and assume that's normal. And what's our sample size here? It's maybe 13. So what's the p-value for the observed outcome using the normal distribution? So we had 8 successes. All right, so x is 8. So we could draw this in and say here's 0.5. And we observed 8 out of 13, whatever that turns out to be, bigger than 0.5. So the p-value is going to be the area under the curve down here, but since this is a two-tailed test, it's also going to be the area under the curve down here. So this is half of the p-value, and the other half is down here. So how do we find that p-value? We need to find, first of all, .14. Let's just copy all this stuff. So pi zeros, we have 0.4, sorry, 0.5. And now our sample proportion P is going to be equal to, I'm going to change this, make that P, let me call this X. So X is 8, N is 13. P is equal to X divided by 13, so 0.61, and so we want to know the area under the curve bigger than 0.61 or less than 0.49. So we're going to get that by saying our let's see, what do we need here? We need, so this z value is going to be 0.61 minus 0.5 divided by the square root. Let's do, z is equal to 0.61 minus 0.5 divided by square root of 0.5 times 1 minus 0.5 over 13. So what's that z value going to be equal to? So here we have, let me change that to an E. So I have E21. E21 minus A21, so 0.61 minus 0.5 divided by the square root of 0.25 times 1 minus 0.25 divided by n. So the z value is 0.83, so that's correct. And we don't need, maybe we'll need that thing later. But so to get the p-value, we just want twice the area to the right of that thing, so 2 times 1 minus norm dot s dot inverse dist. Put that number in, comma 1. So our p-value should be about 40.5%. So let's throw that in. The 5% level of significance in the right tail. And a right tail test is a coin biased towards heads. So now they're saying right tail test. They didn't specify that before, so we might have to change our p-value if we get it wrong. I think this is right though. Let's double check it. Okay, so maybe that's one of the sources of your troubles here. So let's get rid of the 2 on here. Even though we set it up as a two-tailed test, they pulled the bait and switch on us, which is not very cool, but sometimes that happens. So now let's try it. Okay, so there we got it right. And the 5% level of significance is the coin biased towards heads. In other words, if we have 13 flips of the coin, how many do you expect to be heads on average? Well, 6.5. We saw 8. So is that difference significant? Statistically significant? Well, it turns out it's not, because p-value is 20%. All right, so finally they say use Excel to calculate the actual probability of that's approximated by this p-value. So in other words, we want to know binomial probability that x is greater than or equal to 8, and this is going to be equal to 1 minus binom dot dist. So 1 minus binom dist, we're going to put in x, which is that number, minus 1, comma, probability of success, 0.5, sample size is n, and I've got those in the wrong order, so I'll change that to 1. So let me change that to an A, and that to a C. So the real probability is 29%. So you can see that this approximation with the normal is not very good. And we'll say that's an approximation. I mean, they tell me right here how to do this. 1 minus probability x is less than or equal to 7. Think back to what we did in chapter 6, where we had binomial random variables, and we did just that with the binom.this function. Okay, so last one, number 16. All right, a quality expert inspects 420 items to test whether the population proportion of defectives exceeds 0.03 using a right-tailed test. Alpha equals 2%. So this is homework 7.16. The null hypothesis is that pi is, okay, so if we're testing whether the population proportion of defects exceeds 3%, that's telling us what the alternative hypothesis is. Right, so they've got this machine that produces these, whatever it is, and they're checking these things to see what the defect rate is. And the machine should be doing what it's supposed to be doing, which is producing less than 3% defectives. So the null hypothesis is that mu is less than or equal to 0.03. The alternative then is that pi is greater than 0.03. So we've got what kind of test? Is a right-tailed test. Alpha is 2%, and we have 420 items. So this is just like the other questions we did. What's the power? Oh, sorry, they're asking us the power of the test. Okay, so this is maybe gets a little bit more involved. Let me draw this picture again, but do it like this. So here's 0.03, and the power of the test is going to be the probability of making the right decision when the alternative hypothesis is true. So if this is alpha right here, that tells us the critical value is that fixed number, and that's going to be equal to 0.03 plus 2% in the tail. What's that going to be? I don't know what that value is. We'll have to look it up. But whatever it turns out to be, call it z, so 0.02 times the square root of 0.03 times 1 minus 0.03 all over n. So that's going to be the critical value. If the real mean is 0.05, it's really 5%, then I want to know what's the probability of being in the rejection region, because I want to reject. So the power of the test is this area under the true distribution inside of the rejection region. So I need to know this critical value, and then once I know the critical value, life's easy. So let's come back over here, and I think we can just rip this one off. This was a right-tailed test, right? Oh no, we want a proportions test. Sorry. Let's get this one. That was a left-tailed test. We'll have to adjust that a little bit. All right, so we're going to call this. So we have 0.03, it's pi 0, and we'll call this pi 1, 0.05, that's the true value. N is 420, alpha is 0.02, and we actually want 1 minus this thing because it's now a right-tailed test. Right, so our critical value is 2.05, and if we convert that 2.05 into the p world, this should be right. We get A25, so that's 0.03 plus E20, that's z times the square root of 0.03 times 1 minus 0.03 over 420. So our critical value for the p is 4.7%. So this is 0.047. And if that's the case, then we want to know what's the probability of being to the right of that. So this power is the probability that p is greater than 0.047, given that pi is 0.05. Okay, so let's come over here. We have, let's see, we don't want that one. Let's just find the power. All right, so the power is going to be equal to 1 minus norm.s.dist. The z value is going to be p critical minus pi 1, which is 5%, divided by the square root of pi 1 times 1 minus pi 1 over n. And then I need a comma 1. So the power is 60%. Let's just pull this out real quick and see what it is that we're. So we're looking at the z value. So this is the z value. Call that z power. And so then the power is going to be equal to power is going to be equal to 1 minus norm dot s dot dist, that number, comma 1, so 0.6. So this is saying we have, if this is the mean, then we're saying in the z world this is negative 0.27, and we want to know the area bigger than that, and it turns out to be 60% or 61%. Okay, so I'm going to plug that in, and I'm going to check it out, and you'll see I got it right. So for the other parts, it says let's just change the proportion from 5% to 6%. So all I have to do is come in here and copy that, paste it, and then change this to 0.06, 0.07. And my power, you can see the power going up. Okay, so we'll see you guys a week from today. Last day of class is next time we meet, and